All right, let's start out with definition of set. You talked about sets all your life probably. We usually use capital letters, like the not scripts on it. A set A for sets is a collection of objects. So an example, set of all plebes, and put an A equals at West Point. That's a set. Make sure what we're going to do is don't fill in the blank right away. Go to take good notes, everything, and then we're going to pause. The fill in the blank was Liz Ake's idea. If you know Liz Ake, she was trying to break me several times, say, stop, ma'am, stop, you're going too fast. I will go fast. So what I'll do is every once in a while I'll pause, and then you'll take a deep breath, look at the notes you've taken down, and fill in those blanks. When something's not understood, you can raise your hand right away and say, ma'am, I just don't get what I'm supposed to fill into this blank. Got it? Let me change color, so. Here's another example. This one's chock full of notation, and what this means is it's the set of functions f of x. That's what the first part means. After the colon means such that f goes from the real numbers, that little symbol means real numbers, to real numbers. That means that the things you can put in the domain is the real numbers, and the outputs are going to be the real numbers. That's what that arrow means. With f at 0 equals 1. By the way, I'm teaching two classes. One of them is you guys, the other one's topology. And everybody in topology has had several proofwriting classes. So sometimes I might be coming in here and using notation because I'm just used to using it that you've never seen before. You got to do a Liz Ake at that moment and say, man, stop. We don't know what you're talking about. All right, so the way to think about this is these are the folks you're letting in. So think of this thing as being a club. These are what the members look like. And so everybody in this club is a function. I did this on purpose. I could have chosen some easy set. I wanted you to see something where I can actually collect up all the functions. It doesn't say it's continuous, just any function goes into the box. But then you say, wait a minute, not all of you can get into here. These are the restrictions. The functions have to be something, so complex value functions, they're out. So this tells you what the members look like. This tells you the restrictions on those members. So it's like you're bouncing at a club, and you're letting people in, but the folks that are let in are functions such that the intercept is 1. So one of my favorite questions, and I don't know if I've asked you this one. I don't think I've done it. I'm going to. I'm going to give you a set and then ask you for members that are in that set and members that are not. That's one of the first things I think about when I read something, like, oh, what's in this set? What are the objects? I asked the topology class that yesterday. What are the objects in this set? And they do exactly per second. It takes a minute to actually think about it when someone writes up notation like this. Right, questions? Can I peek at this? I don't even remember. So I must have had notes somewhere. Okay. I'm going to have to let you guys pause and fill in all the stuff from the last class too.
And when you're looking, say you're about to start or you're trying to do a proof, is what's in the set kind of narrowed down? Like, does that kind of get you started?
That's like all the, there's like a lot of preamble work that you have to do, really thinking through what you're reading. The proof guide helps you do that. It's just like, I think the change in how you think is, think about volumes of revolution. You get a problem, you're like, this method, washer method, and you just go, right? You just go down this pipe. But in a proof, you have to kind of read that and spend about, it depends on the complication, how complicated it is, but you have to breathe a little bit and think about what it's asking you to do. And if it's asking me something about sets, the first thing I think is, can I come up with examples that are in that set that I can concretely think about, and things that are not in that set. When I think of examples, I think of non-trivial examples, like that one's non-trivial. In books, they typically give you trivial examples. Like I could have just given you the set of real numbers. Like that doesn't teach you anything. Right? This one taught you something. Like I have weird things in the set. So yeah, you do have to think about all these things ahead of time. I would say that the writing of the proof is a lot easier than the preamble stuff. The preamble stuff is just organization. All right, next definition, I think I give you a subset. I'm going to be good too because there's two notations. I'm going to change that. Even if I had notes, I wouldn't follow them anyways. I just go. This is the definition of set containment. Notation is a It's kind of like less than. One set is inside the other, and this means that the set could actually be equal to that other set. I always want to, there's some things about math I just love. Think about the rational numbers. There's a lot of rational numbers. Can you give me the first rational number after 0? What's the first rational number after 0? Whatever you're thinking, I'm going to divide that number by 2. So there's a lot of rational numbers, but there's as many rational numbers as there are natural numbers. And you can prove that. But the real numbers, you can't do that. There are actually more real numbers than there are rational numbers. But if I fill in all the gaps, all the limit points, that's what's missing, is that you can have sequences of real rational numbers that converge to something that's not rational anymore. If you fill in all those blanks, you get the real numbers. So we say the rational numbers plus all its limit points is equal to the real numbers. Where was I going with that? There's an example of where 2 sets are equal. And you might have to prove it. If you really like pure math, you'll have to prove that someday. That's a fun proof. Because when I say and a set is contained in another set, and then there's this equal sign, you're like, what would that be ever used for? I just gave you an example where it's used for. Something that totally twists your mind. Sometime in the semester, I'll show you proof that the rationals are countable. That's what we mean. Like, there's as many rational numbers as there are natural numbers. But the reals are not.
It's natural numbers, yeah.
Natural numbers 1, 2, 3, 4, 5, the counting numbers, the things you put on a number line. I didn't do that with you guys last time.
Does that include negative numbers?
Integers are negative numbers. I'll do that next. I thought I did that with you guys.
Positive integers.
I might have just waved my hand, so pause me. Remind me right after this. Okay, so this is the formal definition of what it means to be a subset. You might have seen something called Venn diagrams before. I sometimes hear non-math people talk about Venn diagrams. You'll see something like this, a set B like this, and a set A inside it. You've probably seen that. Has everybody seen that? You're not very talkative. Can you just make puzzled faces when you don't understand me? It's like, I need some feedback. So you've seen that, yeah. I've seen this like in social science stuff. They have seen people make these things. Right. I'm actually not going to use Venn diagrams to like get the ideas for proofs. I'm going to just get you back to fundamentals. Whenever you have to prove A is a subset of B, you start out with this: if X belongs to A, then X belongs to B. That's the definition. If X belongs to A, then X belongs to B. That's a definition of A being a subset of B.
And that notation between X and A, that's just belongs to.
Which one? Oh yeah, yes, belongs to.
So then A can be a subset of itself.
If A is a subset of itself, then it's, yeah, A is always a subset of itself, right? Yeah. I'll give you one more definition, then I'll pause and let you fill in the blanks for the proof from yesterday, day before yesterday, and I thought it would be easy to teach foundations and topology together, but it's not, because I think I said things to you that I said in topology. So, you guys, I'm going to count on you to stop me. All right, so before I do the one more definition, these are the symbols. The natural numbers has an N. By the way, these are all on, I'll show you both for LaTeX, for tech, and also for, you can pull it down in the equation editor. If you go to scripts, you'll see these symbols. I think they're cool symbols. What that is 2, 3, ... Just the counting numbers. I always think of little kids counting for the first time. 1, 2, 3. We actually, in my house, we built a number line with paper stretching across the ground, made it really large so that when the kids started learning how to count, we just put 1, 2, 3, 4 down the line. And then one day I said, okay, there's numbers in between the 1, 2, 3, 4, the fractions. So we put in the rational numbers. And then we stretched out the number line to the other side. They could walk down back and forth on that number line and went back the other side. -1, -2 down the other side. My son took foundations from me, and the whole class was staring at him when I was telling the class this. And I might have told them that I gave him crack cocaine, and they looked like they felt sorry for him. They were feeling sorry for me. And then one day I told my daughter, hey, look, there's actually these numbers that there's actually holes inside the rational numbers that are not filled in, like square root of 2 and pi. And that's really cool. Okay, so that's N. The 2.7 thing? So yeah, on the number line, I'd point in and say pi goes here, e goes here, square root of 2 goes here. It was a party at my house all the time. So that's integers, natural numbers, and then next one is Q for quotient. Let's see. Let me put that in your new set notation. This set of P over Q such that P and Q are not in Z and Q is not equal to 0. Union 0, and I'll tell you what union is in a sec. What's that? And then we got our see, this is, I just did all your math education, all your life. You started out with N, 1, 2, 3. Then one day somebody told you there's negative numbers. And then one day you got taught how to divide. And then when you went to, probably now in 7th grade, they start teaching you algebra, right? So one day you did real numbers. So this is your math education.
So the Q is real numbers?
The Q is the rationals.
Rational. And that includes 0? Is that what that is?
Yes. A couple more definitions, and then I'll pause. So you want me to pause. Liz did a good thing for you guys. If something's in the union, it's either in A or B. It's a set of X such that X is either in A or X is in B. Two more. Okay, here's another one. Intersection. Did you guys have to do, because back when they changed math education a lot, when I was little, we'd always have to do unions and intersections of sets by drawing the football in between the two circles, and then every class would start out with set theory. I think they changed that now. So these are all new things. Set theory is the foundation of theoretical math, and theoretical math people were writing textbooks. So at the beginning of every textbook, we used to have these axioms. They're not there anymore, maybe. I'm abusing letters, so I'm not gonna use the X again. Intersection, it's in both of them. So when we had to do union, when I was little, we'd have to like color in both. That's A, union B.
You did that in stat, too, is it?
Oh yeah, for probability. But I remember doing it in like elementary school.
I don't remember really anything from my math abilities.
This was part of my like algebra, geometry, like all those classes.
Somebody gave you a textbook that had that in it.
My textbooks were all from like the 70s.
That's it, yep. So there was like a reform, it's actually called the Math Wars. There was a reform back in the 90s where math educators got involved and said, you know, this is not what students need, and you're actually letting students pass by without really knowing what they're doing. You need to stop doing this. And theoretical mathematicians said, you guys are making things easy, you're being too soft. And there was like this war between the two groups. Okay, so let me pause there and let you fill in the blanks. And some of it should be the stuff we did from the last class, so it'll take you a little while to get through, but if you took good notes, you can go back to your prime number things, and I'm here for questions. So you can ask me questions and fill in. You should get all the way up to, next time I'll print out one for myself. All the way up to 18.